Okay. So, because of what I discussed earlier, inverse is a very complicated problem. So many a times, even though we have the direct formula, using an iterative method like linear regression can come to our benefit, especially when we are talking about huge amounts of data. So let me now shift gears. In last class, we saw implementing linear regression. Now let's see how we can actually use it for a data science problem. So here the data science problem we're looking at is the house price prediction. I'm running this from my Kaggle notebook. Let us, yeah. So we load some packages. This is the description file of the data. Let me also maybe just first talk about the problem statement and then come here. Okay. So this is the competition. This is the getting started for linear regression, getting started for regression data set, in which you basically having a data like this, where we have, we go down to train. We have all these features: ID, MS subclass, MS zoning, lot frontage, and so on. And what we are trying to predict by using all of this data is something called as pricing. So let me. So given all of that data, so there are 81 features. We are trying to predict something called a sale price. It says that, okay, given all this data, the price of this house is 208,500. And thus it becomes a linear regression problem. Thus it becomes a regression problem because we are taking the different features and we are trying to come up with a variable which is continuous in nature. It is not discrete. So there are many values and it is impossible to have a classification problem at this time. So it is much easier to represent this as a regression problem. And for this, they have given certain data. If I go to data description, this is a text file. This explains what the different features are and if they're categorical or not and what values are there. So let's say this option, MS subclass, it identifies the type of dwelling involved in the sale, and they are given some code. The code 20 represents one story 1946 and newer all styles. Code 50 represents one and a half story finished all ages, okay, and so on. So there are different codes given. Uh, there are many categorical features. There are many linear features, numerical features. So let's say, for example, here, dot frontage is a numerical feature. Dot area is a numerical feature. Street is categorical, and so on. So there are multiple categorical and numerical features associated with this data, and we have test data for which we have all this information except for sale price, which we need to actually predict. So that is the data at hand, and here I'm first loading the description file, the data description.txt file, and I'm just printing the contents of that file here, which is the same file that we saw in the data section of the competition. And we have it here so that we can use it for reference if we need to implement something. I load the data. So there are two CSV files, train.csv and test.csv. So within Kaggle, if you create notebook by joining the competition, So there will be a section here called as join. You join the competition, you go to the notebooks and you create a new notebook. That new notebook will already come with links to the input data. So I have the input data here. I can just copy on the train CSV test CSV. If I copy the file path, then I can paste it here so that I can read that CSV into df train df test. If I print df train or print the head for df train, you can see that there are 81 columns. So 81 columns means it will not even print everything. Uh, these are the first few columns, last few columns with sale price as a prediction that we need to. And this is a DF test with 80 columns that is not having sale price, and that is the thing that we need to predict. So in the data exploration phase, it would be interesting to answer certain questions. First question that I ask is, so this is some approach that I'm using since some time now, which is basically rather than directly attempting to do some exploration on the data, I generally ask certain questions and then I look for pieces of code that will answer those questions. So in that way, I'm a bit more focused on what I really want to do. Otherwise, I have seen myself to get distracted very soon. So when I start exploring your data, you would think to do so many things, but we don't have a strategy of implementing. So uh, this approach so far has given me some good results. So I'm focused. As soon as I get my answer, I know I don't need to explore further. This is what I need. I stop there. Then I ask the next question, try to attempt solving that using code again. And like this, over a period of few questions, I have answered the major points. Uh, and I've seen generally these questions for most data sets are very similar. So the first question in exploration is, what are the features present? How many of them are numerical? How many of them are categorical? Maybe can you tell me how this information will be useful, or what could be the use of having dividing into numerical and categorical features?
We train that numerical separately and categorical differently, and we used to scale that to 0 to 1.
Hmm,
We
right.
different things in different types.
Exactly. So part of your answer is right. Actually, we train the model together. Like us, by training the model, both numerical and categorical features are used. But one step before training is doing pre-processing. And pre-processing of numerical features are separate than pre-processing of categorical features. As you said, one-hot encoding is something that we'll be using only for categorical features, not for numerical features. And for numerical features, we would use feature scaling, like standardization or min-max scaling, and that will not be used for categorical. So since these are different processes we need to do on the different kinds of features, it makes sense that we know which are the numerical ones, which are the categorical ones. So here first I look at the DF columns. So, and see, okay, so there are so many columns for us. If I look at dftrain.info, we get a sense of the column number, column ID, how many non-null values we have, uh, and what is the data type. Okay. So there are many of these guys. Uh, so if you look at the different types of data types, let me show you. Do I have it here? Okay. If I look at the different data types, there are three categories. We have integers, objects, and floats. Okay. So can you comment on looking at the data type itself? Can we say something is an integer, something is categorical, or something is numerical?
Integer and float are numerical and object is categorical.
Okay, excellent. So integer and float generally are numerical, and objects generally would be categorical in nature. Right? So I'm saying generally purposely, and I'll show you why. Let me go ahead. So first I say, okay, the features with data types objects are definitely categorical. And additionally, there may be some features with integer or float that may be categorical as well. I'll give you an example. When I was going through this file description.data, I can see this feature MS subclass, and this MS subclass has these values 20 to 190, and even though there are numbers, even though these are integers, I know that these integers are actually codes for representing something. So they are actually categorical values and not numerical values. This is definitely categorical. But going through this, there was some list of features which had numbers but still were categorical. So like for example, this one, overall quality, it has numbers, it has only 10 values, but these are categorical to represent very poor to very excellent and so on. So I say, let me take all the object values. All objects are definitely categorical features. So I take df, let me do this. So dftrain.select data types include only objects, gives us all these guys. And I want them in a list and I want to store them into cat features. So I convert, pass this output of that to a list and then store it into cat features. So cat features standing for categorical features. When I execute, it creates the categorical feature. On inspection of the remaining features, the following are categorical as well. So we have MS subclass, overall quality, and overall condition. So I add that as cat feeds num and add it to the original list. Now that I have all categorical features, the way I can get numerical features is take all the columns, take the set of all columns, from that subtract categorical features, and from that subtract ID and sale price as well. So sets are very useful for things like this because it's like a Venn diagram, and from the list of objects you can directly subtract these days, and I take that into a list, and that is what my numerical features are. So I just print the number of numerical features. There are 33 numerical features. These are the values, and there are 46 categorical features, and these are the values. So that answers my first question. How many features are there? How many features are present? How many numerical? How many categorical? So we have a total of 81 columns, 33 numerical, 46 categorical, and two guys are ID and sale price. So these are actually not features. ID is just an identification number to know which to differentiate the data points, and sale price is our target label. So we have these many features: 33 numerical and 46 categorical. Next simple question is how many data points in train and test. So we just print the dftrain.shape, dftest.shape. We can see that there are 1460 data points for training and 1459 data points for testing. So our test set and train set are in fact 50-50%, very close to equal points. So when we are actually doing it, when we are attempting a challenge on Kaggle, and this is something that I got confused with. So when I started out learning data science, I was introduced to Kaggle and I started practicing here. And here, as Kaggle uses the test set, I thought that this actually means the test set, which now I realize here is this test set is not the same test that we call test set while dividing the data set into 3 parts. This test set is something like Kaggle needs an evaluation for to see how good you're doing. Normally, my test set, I should have the answer for my test set also. So using this dftrain 11460, this will be all the data points that I have. And then I would have to further divide these data points into train, validation, and test so that I will do my analysis. So even though this is called as df test, this is truly not df. This is not the same test as we use for evaluation of the model. This test is actually used to evaluate evaluate how good or bad we are doing with the entire thing. And since we do not have answers to this, we have to rely on what Kaggle is saying to how close our model is. So it's a small difference there. Uh, if I had the answers for these guys, okay, then I would truly call it as a test set. Okay. So now we have 50-50, but this 50 is a different. I hope I'm making the point clear that this is not truly a test set because we cannot find the evaluation for this guy. Going ahead, are there any missing values? So let us check. So you dftrain.isnull.sum.sort values by descending order. You can see that there are many missing values within the train data, and there are many missing values within the test data as well. Okay. And if you remember, we have 1460 data points in the train, of which 1453 data points of pool QC is missing. Okay. What would you say? Is this feature important then or not? Out of 1460, we have 1453 missing.
No, it is not important.
Yes, it is. Go on, Anand. You were saying something, but
No, we can remove. That is better here.
yeah. Okay. So this is what I originally thought, but then I thought let me also verify why it is missing, and based on that we can get some more idea. So uh, I went ahead and said let me explore the missing values. So now I'm entering into data preprocessing. We said let's first deal with missing values. So pool related missing values. So if I take pool QC, which is pool quality, and do a value counts on it, I can see that I have 3 examples of good, 2 examples of fair, and 2 examples of excellent. Let me on one side open the data description. And here we are looking for pool QC, so that we search for pool. So there are 2 features actually related with pool. One is called as pool area, that tells you what is the pool area in square feet, and the other is called as pool quality, which tells us what is the quality of the pool. So we have these are the values that the pool quality can take. Excellent, good, TA standing for average or typical, FA for fair, and NA for no pool. So when I look at this, we see examples of only good, fair, and excellent. No examples of average and no examples of NA. Then I said, okay, let me also look at uh, pool area, where the pool area is 0, and what is the pool quality. So when I searched for this, that is from dftrain, I shortlisted all the cases where we have pool area as 0. We saw that there are exactly 1453 examples where the pool area was 0, and for which the pool quality was NA. So these are the 1453 missing values that we have. So looking at this, we can easily conclude that these 1453 houses don't have pool. Okay. Since their pool area is 0, they don't have pools. And since they don't have pools, ideally what should have happened is the text NA should have been written there to represent there is no pool. But the data shows as missing values. So I said, okay, this is very simple to fill. Instead of missing values NaN, I will replace all these missing values with the value N, which stands for not applicable. So I do it both for the train and test. And now when we look at the remaining missing values, we can see that the next feature to target here is miscellaneous features. And I said, let me go ahead with this. So going ahead, again, I do the same strategy. Let us look at missing features. I can see, okay, there are 49 shed, 2 as garage 2, 2 as other, 1 as 10C, and we have other missing values as well. So I say, let me look at miscellaneous features. And these miscellaneous features can have these options. NA or none is one of these options. That is, if you don't have an elevator, if you don't have a second garage, or a shed of over 100 square feet, or a tennis court. If you don't have these things, then you put any. Now, I would say that these things are very generally rare for a house, and thus many features will be NA. And here also NA was not defined. So,
Like a small doubt.
go on. Tell me.
This data, it might be missing. Also, it is not present in NA. Both are, we can't. If it is NAN, then it will be not applicable. How you came up to that conclusion?
For the first case, you understood how I came here.
Yeah. First case, okay. It's
Okay.
clear.
For the second case, now I have, so generally for the second case, I would say I have, okay, first is looking at the values that are there. Okay. And this gives us a hint that these are generally rare things to have in a house. Okay. Not many houses will have a tennis court. Not many houses will have a 100 square feet shed. Not many houses will have a second garage, and not many houses will have an elevator. Okay. So these are generally looking at this, you would say that these are already rare values. Okay. Finally, we also see that there is an option called as N. So if my data is actually missing, it would make more sense for me to go for NA rather than any of these, because I have also explored the data, other parts of the data, and there is very less correlation between this part, elevator or other garage or other things. And the data that we do have, we have out of 1460, we have only these many values as full. Okay. If we try to take, so generally a strategy would be replaced by mode. So if I replace by shed, okay, what I'm basically saying is that most of the houses will have a shed over 100 square foot area, which is very unlikely.
Yes.
So in this case, I would go for, let me go for one of the options that is provided with the miscellaneous features. And this option is not executed for the data. And hence I go with let me replace for any. Also, when you explore this data, you will find out that even though the data description says that NA is a valid option for many of these features, none of these features actually use NA, which tells me that in the process of transferring the data from one form to the other, one of the pipelines have assumed NA to be NAN, and thereby we have a lot of missing values here.
Okay.
So based on these hints from the data, I said that, okay, let me fill with NA. Also, I explored other notebooks that other data scientists have done. They have also used the same strategy. So I said, okay, it is then safer for me to replace with NA. Okay, going ahead, we have Ali. So again, same strategy. I explore alley. I find that many houses will not have an alley. We have the houses that do have. We have a gravel alley or we have a paved alley. So I replace that with NA. So most of this data filling will happen this way. Let's go to fence and say fence also replace with NA. Fireplace quality and it goes to NA. This is the, now comes the next, the only interesting data filling case, that is lot frontage. All the other values will be actually filled by NA. When I come to lot frontage, I see that there are 259 missing for home for train, 227 for missing for test data. And going ahead, if I look at what are the other features associated with lot frontage, I can open this and see that there is lot frontage, lot area, lot config, and lot shape. Maybe before going ahead, do you know what lot frontage stands for?
No.
I'll just tell you. So lot frontage in the description gives us the idea that it is linear feet of street connected to property. linear feet of street connected to property. Okay, have you got this now?
Yes, yes, understood.
So let's say if I have this is my house, and this is this line, and this line are street. Then my linear feet connected to street would be this distance plus this distance plus this distance, because the three parts of my house are exposed to a street. One part is not exposed to a street. That is what we mean by lot frontage. So here, uh, related with lot frontage, we have lot area, lot config, and lot shape. Lot area is just the area that your house takes or comes under your house. Lot config and lot shape again are interesting things. So let us look at lot shape. So lot shape, there are four examples: regular, uh, IR1 that is slightly irregular, IR2 moderately irregular, and IR3 irregular. Okay. For which of these will it be easy to evaluate lot frontage? Sucha, did you say something? I saw the mic.
No, no, no.
Okay. Okay. So regular would be basically, I don't know much, but I'm estimating that regular would mean a rectangular house, so that I can easily count the size. Irregular or more regular will mean something like this. If I have a house built on an uneven space, that is maybe it has an oval shape or something, then to evaluate street linear feet of street connected here, it may not have a one-to-one translation. It may be a bit more complicated to evaluate that. That is what I thought lot shape means. And there is something called as lot configuration. So whether you are an inside lot, corner lot, cul-de-sac, frontage on two sides of property, frontage on three sides of property. Again, depending on this also, a lot of our lot area will be dependent upon. Cul-de-sac is basically you are a house at the end of the street. So if this is the street, then you are a house at the end of the street. It is called as cul-de-sac. So this is the features related with lot frontage. Uh, for now, what I decided was I will not incorporate lot config or lot shape into the prediction of what my frontage should look like. And I said, let me just take lot area and let's see how lot area may be correlated with lot frontage, so that I may get some idea or some sense of how these are working out. So first I take a scatter plot between lot frontage, lot area on the x-axis, and lot frontage on the y-axis to see how the data is distributed. Can you make some comment looking at this plot?
What comment? I don't know.
Okay. Let me then ask you questions. Okay. What is the range of lot area? So this is all the units are in square feet. So lot area goes, what is the minimum lot area? What is the max lot area?
0 to goes to 2 lakhs.
2 lakh square feet, right?
Yeah,
Okay.
only 1K.
Yes. So is 2 lakh square feet natural? Or do you think there can be a house which is as big as this?
If he's super rich,
So I'll give an example. So the house that I'm renting right now is a 2 BHK, and it has 1500 square feet.
yeah.
So you have seen my house, Anand, right?
Yes, 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 yes.
Yes. Now just imagine a house 2 lakh square feet.
Yep.
Not possible, right?
Not possible.
So definitely looking at the data and having some sense of how big houses are, this is clearly an outlier, right? So
Yep.
this point here, and there's just this one point. So we know that this is an outlier. Can you point some more outliers?
More than 300 in lot frontage.
Yes, more than 300 feet in lot frontage. 300 feet in lot frontage is too much. I remember my 100 feet race uh, in school. 100 feet is pretty long for a house, and 300 feet of lot frontage is again huge. So I know that at least these 3 points are outliers, and I also get a sense of an idea that these are outliers because everything else, or 99% of my data, is together, and these are 3 points which are having, they are separated by a very good margin from these points. Had I found maybe more points in between leading up to this point, then it would be doubtful to say these are outliers or not. But at this point, understanding how houses are, and seeing this huge gap between these points, I can know that these are outliers. So we have to deal with them. What can I do with these outliers? What did you say?
We can remove that.
Yeah, great. So one option is I can delete them off, or I can do something called I can bound their range also. So what I do is, in this case, I don't delete, I bound their range. So I say this is the closest data point here, and I pull this point from here, I pull it to this point. So I first do a value counts on lot area, sort values, so that I can see what the exact value is. So the exact value is this, and I see the closest value we have is, in fact, I see more missing values. You see, I have not just this as lot area, I have lot areas in between also. 164,000, 159,000, 115,000, and then 70,000. These points are not shown here because I found that these are the same points for which lot frontage is missing. And since lot frontage is missing for these points, uh, uh, the scatter plot cannot plot it. So it leaves it as empty. So let me, okay. I also then link the lot area with the corresponding lot frontage. So now I have sorted according to lot area, and I'm putting the lot frontage of these properties in front of them. So this guy has a lot frontage of 150. These three data points have missing values. This 70,000 lot area has a lot frontage of 62, and so on. So what I first do is I say any lot area that is greater than 70,800, I will limit at 70,800. So I execute that. Now I look at the plot. I can see that this x-axis has become more confined. Y-axis not changed so far. So I said that let me again now sort according to lot frontage. So we have lot frontage of 313 at this, 313 at this, and so on. I say, okay, let me limit lot frontage to 185. And after doing that bound, now when I look at the scatter plot, I see more of a confined area. In fact, I could also consider all these guys as outliers as well. But I said, let us not go, let us not manipulate too much of our data. Let's consider this to be the true scenario. With this as the true scenario, I do, using Seaborn, I do a regression plot. And what the regression plot does is, along with scatter, it draws a line that shows some relation between lot area and lot frontage. Okay. And I said that, okay, I will use this line, I will use a regression kind of a line to help me find the missing values for lot frontage. So the 259 missing values for lot frontage, I have their corresponding lot areas. So what I can do is I can train to fill the missing values. I can train a regression model which takes all the known data. That is, will take data for which lot frontage, lot area both are available. Use that as train data. Train a linear regression model, and use the linear regression model to predict for the cases where lot area is present but lot frontage is not present. Is the strategy clear?
Yes, but why we are not using that categorical data also to do this prediction?
Uh, why we are not using this guys, right? Uh,
The
lot config and lot shape.
Yeah, if it is missing means maybe they can answer it.
Yes, probably. The next step could be doing that. I simply did not use because I thought it to be hard. So I thought I will go for an easy solution. But yes, we can use lot config and lot shape as well. So here, what we would have to do is we would have to do one hot encoding for lot config and what lot shape, and then use numerical dot area, and those will be the variables we can use for dot config. And in fact, let us try that. Let me go down. So I'll just tell you what I did first, and then we will try the second option as well. So in this case, I said, let me, from scikit-learn's linear model, let me take linear regression, and I will divide this data into two parts, lot not null and lot null. That is the cases where lot frontage is missing, I will keep into lot null, and the case where lot frontage is not missing, I will keep into lot not null. Why these two? Because one will become my training data, one will become my test data, or one will become where I want to predict my model. So, okay. Then I say, let us take all the cases of lot not null. So these are the cases for which we have lot area, and these are the cases where lot frontage is missing. So there are 1201 such examples. Was this the number we started with? Let us see the missing data ahead. Okay, so we have 259 missing. So I think there are some examples of, no, we have 259 missing lot frontage here. And here, not null, we have only, there we go. Yeah, lot area, we have only 1201. It means, okay, 1201 plus 259. That's right, 1460. We started off with total 1460 data points, of which 1201 are values which we know the answer for, lot frontage, and 259 are missing. That the number adds up. So we have our lot area. I create a linear regression model, store that into LR miss for linear regression miss, fit this model with this as the train. So for train data, I'm just taking lot area, converting that to NumPy, reshaping it to -1, 1, and it was just a requirement for scikit-learn's method. So we had to do this. This is the X. Y is this value, that is lot frontage for the not null. So we have X and Y, and we train our linear regression missing data. Once we have trained it, then I say, let me predict it for the cases. Let me predict it for all the values. Okay. So I predict this answer for all the values, and I end up with lot frontage prediction. And then I use np.where. Okay. np.where. Do you remember the np.where function? It takes three inputs. The first is a Boolean yes or no. The second is what to return if Boolean is true. And the third is what to return when Boolean is false. So we are doing lot frontage is null. So it will have true values whenever there is a null data. Whenever there is null data, replace by this number, return this number. And when this is false, that is we have actual data, return this number. And then populate that into lot frontage. So when I do this, uh, okay, for train, and when I do this for test as well, then we end up with, and I delete this lot frontage prediction variable. We see that all of our lot frontage is now taken care of. Okay, we don't have any missing values for lot frontage in train or test. Is this fine so far?
Yes, it's
Okay. So then let's also try to see what we can do so that we can add those other ideas. So let me reset the model and execute here because I have populated lot frontage. Let us execute till this point. So we can simply do a restart session. And for this cell selected, you can go to run, and there's an option called as run before. So in Kaggle, I can just run all the cells till that point. Okay. So we have run all the cells till this point. Let me execute this. If I quickly check if do I have missing values in train, so df train dot is null dot sum dot sort values and ascending equal to false. Great. So lot frontage is missing. So we can use this idea. The regression is fine. This part is fine. Okay. So now we are supposed to extract not just lot null, but along with lot null, we will extract lot config and lot shape. When we do that, we can see, okay, these are the three data points that we will be looking. Lot area, lot config, lot shape. I will store that into xmiss. Now this xmiss I cannot directly give to my data. I cannot directly give to my model. So we have to do certain things with this before we can give it. First, we need to do one-hot encoding for these two features. So let's do that. So it's so I think pd dot get dummies. I've forgotten the code, so let me write help of pd dot get dummies. So we have to give first the data. My data is xmiss, then prefix. Okay, so let's the prefix be. Okay. I'll give two prefix because two values we have to manage. I'll write prefix equal to lc for lot config, and let it be ls for lot shape. Next, we have to give prefix separator. By default, it is underscore. That's fine. Dummy NA, that is ID column to include NANs if NANs are. There are no NANs, so I don't need to worry about this. Columns. So which columns are we wanting to do? Like this as columns equal to columns are plot config and plot shape and drop first. Whether to get k minus 1 dummies out of k category levels by removing the first one? Yes, I think this is fine. We will do drop first as true. Okay. If I just execute this, let us see what we get. Okay, so this is what we expect, right? So lot lot config, we have cul-de-sac, FR2, FR3 inside, and lot shape we have IR2, IR3, LS. Right? By doing this drop first, you see one less missing value is there. Means one less column is there. Here I think we had one more column. Let me go to dot config inside. So it has removed inside, and instead of inside, what will happen is, oh no, inside is present. Which one is gone? Corner. This corner is gone, right? So instead of uh, corner, what will happen is when all the four values are zero. So let's say, for example, this case. Yes, this case where corner is there for 9550. see for 9550, when corner is present, all the 4 values are 0, and that also represents corner, right? So in that sense, that is what we mean by drop first is equal to true. So I get this data into, let's miss again. Okay, so now we have our data. We can simply add y miss also. So y miss is pd dot get, sorry, y miss is df green and what we are looking for is lot frontage. So we have our x miss, y miss. That will be the data that will pass here. So now I can, instead of passing this huge thing, I can just pass x miss. With this guy, I think I can pass y miss. And to get the answer, we can predict it for this. So now to predict it, we have to get it for this. But we don't want these guys, we need to move it. So all the columns of this one, that will be our x test. We predict it, and yeah, let me not populate this one. Let me put it as new, so that if we have to go back, we have some way. Okay, let's run this and see. We got an error saying that could not convert. Yes, because okay, because we removed this guy. Let us not remove it. Keep our job a little bit simpler. We'll do xmiss again. Xmiss head. Uh, now what happened? Oh, xmiss. Sorry. 1, 2, 3, 4, and I think now it should be fine. This is a problem. Could not convert string to 4 inside. So we'll have to do pre-processing of this guy beforehand. Let me cut this, add another code. Let's see what this guy gets. So we have lot area. We cannot directly pass this to this. We have to do pd.get dummies for this one and then pass it. So okay, let's take copy it. Let's store it as x all with this one, and we will say x all is basically this, and we'll predict for x all. Okay. So now we will. Okay, so we have lot frontage new. Let us see what is lot frontage new. Okay, all 14, 60 values. So no missing values. So I think we are good. We can even remove this part here. And for here, this guy also we'll have to, for test also we'll have to do this part. So let's write this for test. And instead of df train, we'll do df test. Mhm. Okay, this looks fine. What is the error? Lot conflict. That's true. They're there. No? Oh, do they have some missing values? Okay, let me check. No, they don't have any missing values. Okay, I think we are doing over hard time. Uh, let me explore this on my own, and then I'll come back and we can discuss this in the next class. Is that okay?
It's fine.
Also, what you can do is I will. I think I've made this notebook as public as well. So I can give you the link to this notebook. Is it public? Let me just quickly check. Yes, it is public. So I can share this with you guys. Yeah, I'll give you the link to this notebook. You can spend some time going through this, see what I've done next, and at least try to finish till the data pre-processing. And in the next class, we can discuss from regression notebooks. And if you have any questions, or I would also suggest spend some time in working on any of the data sets we've done so far. No one has given any predictions here. So if you have some time, try to try to work on any of these skills, either Titanic or heart disease prediction or human activity, or the one that we're working on right now, so that you have some more hands-on. Once you do some hands-on, then you will know what you know and what you don't know, and then we can have some discussion around that topic. Okay. So let's stop for today. See you guys next time.
Okay, fine.
Okay. Bye bye.
Bye.
Bye.